Good morning. Welcome to this webinar hosted by ORS Consulting and today's topic about process safety and SIL. So I'm Morten Peterson and is the head of operations in ORS and also the moderator for the session today. So I'll come back to you for a short Q&A session following the presentation by my colleagues. So if you have any questions during the presentation, please send them in using the Q&A functionality on the right side of your screen. So in this webinar today, you will meet my colleagues Thomas Fylking and Baris Arslan, our subject matter experts within process safety and SIL. So I hope that you will all enjoy the show. And are you ready, Baris?
Yes, Morten. Thank you very much. And hello, everybody. My name is Baris Arslan, and welcome to our webinar about process safety and SIL. Together with my colleague Thomas, I will discuss some basic concepts of process safety and SIL, together with some experiences we have from our experiences. And Thomas will present the agenda very soon. Before this, I would like to present my background. I have a Master of Science degree in Mechanical Engineering from Lund University in Sweden, and I have more than 15 years experience, international experience within risk and safety engineering. So my main experience is from oil and gas and petrochemicals industries, but in the recent years, I had also gained exposure and experience within the low carbon industries, such as hydrogen business, biogas, and a number of other industries.
Thank you, Baris. My name is Thomas Fylking. I'm a principal consultant at ORS Consulting. My background is within chemical engineering, and I have a master's degree in chemical engineering from the Norwegian University of Science and Technology in Norway. For the last 15 years, I worked as a process engineer and as a process safety consultant, both within engineering contractors and within operators, both as staff and as third-party independent person to validate assessments and so on. My main experience is within offshore oil and gas, but I've also experience from onshore petroleum and petrochemical industries, and also from a range of low carbon process industries such as hydrogen and biogas. So first, I'll just give you a short introduction about what we will discuss today. We've split our presentation into two parts, where the first part is a brief introduction to the concepts and foundations that our second part is based upon. It's important that we give you a short introduction to hazard and risk concepts, process safety and SIL, and standardization and uncertainty as we understand it before we go into part two, which is some of our viewpoints regards to process safety and SIL. As you probably all know, process safety and SIL are very wide fields, so it's not our intention to discuss very detailed aspects, but rather we'll present some informal overview of some of the important aspects to keep in mind when working with these areas. Hopefully the majority of these concepts will most likely be known to or implicitly understood by most of you already, but we still hope that what we present today might at least inspire some thought and discussion. So the first introduction is introduction to risk and hazard concepts. And as you probably all know, a hazard is a situation that poses a level of threat to life, environment, or asset. We're here talking about hazard and risk from an engineering and asset operational viewpoint, where risks and hazards are related to events of a certain magnitude, and risk is something that you want to minimize as much as possible before you start to manage the residual risk. A risk is defined as the probability that a hazard will turn into an accident. And the traditional way of describing risk is you have a hazard with a certain consequence, and you combine that with the probability of that event happening. This is a bit limiting for the ability to understand, administer, and manage activities and assets, because there are an important aspect related to this, which is the associated uncertainty. All your analyses are based on certain assumptions and inputs, and if you don't understand the uncertainty that are related to these assumptions, your risk picture will not be correct. So based on that, we think that risk should be defined as the consequences of an activity combined with the associated uncertainty of that. Another important aspect to understand is that risk can be reduced or managed, but you cannot eliminate it totally. You'll always have some residual risk.
So I would like to continue on the topic of managing technical and industrial risk. And on a very high level and a basic introductional level, we are talking about three pillars of industrial and technical risk management. So to start with, we are talking about barriers, safety barriers for a process facility and a safety critical complex facility. So you need to have your safety barriers in place. This is rule number one, and this is not open to discussion. So for safe and reliable asset operations, you need to have your barriers. On the top of that, you will have to exercise whatever you can within the area of probabilistic assessments. You need to use data, you need to use methods, statistical tools, and all the other things to understand what hazards are credible and what hazards are not credible, right, for the asset in questions. And this is to complement the barrier configuration, so to say. But one of the key things to remember is that the probabilistic aspects of it are not used to eliminate robust safety barriers. It is rather in place to understand what is necessary in addition, right, to make these barriers even more robust, so to say, for safe operations. So it is very important to understand the probabilistic aspects together with the barriers. On the top of it, what we see is that in the recent years, especially post Deepwater Horizon accident in the United States, the black swan events, which are very low likelihood and high consequence events, they are gaining more importance. So we see that large corporations, chemicals and energy companies, they are developing corporate guidance documents to understand how they can manage the black swan events. Why? Because these events or these hazards are very low likelihood and they typically fall out from the traditional qualitative and quantitative risk assessments. So what you need to understand is that if you don't have a structured approach for integrating the black swan type of events, the risk picture and the industrial risk management for your asset may not be complete.
So based on that, we will give you a short definition about how we understand process safety. And we here define process safety within a Norwegian context, where it's usual to operate with two terms with somewhat blurry and overlapping boundaries, namely technical safety and process safety. But if you take an uncontrolled loss of containment event as a top event in a bow tie, you could say that process safety in this context is related to what happens on the left-hand side of the bow tie, while technical safety is what happens on the right-hand side. So in other words, process safety is related to the deviations in the process that could lead to a hazard being realized as a consequence, and the preventive safeguards you have in place to prevent this loss of containment event. While technical safety, at least in Norway, is related to mitigative barriers and means to minimize the consequence after you have an uncontrolled release event. So what's also important here is that within process safety, as we're going to discuss it today, we're talking about major accident hazards. We're not talking about HSE-related events such as slip, trips, and falls. We're talking about the systems and safeguards and barriers you have in place to prevent releases that could cause a major accident hazard, such as a fire or an explosion or release of toxic substances. So within this framework, process safety, as we define it, is the technical and organizational measures that you have taken to prevent process accidents. And it's a framework for ensuring that the process design envelope is protected and has resilience against system failures and degradation. This brings us to the first key principle of process safety, which is that no single failure, either operational or equipment related, shall lead to any unacceptable hazardous situations for either personnel, environment, or asset. As Baris mentioned earlier, there is a barrier versus or prescriptive versus a probability approach to safety. But in process safety, these approaches need to be combined because you can't design a 100% foolproof design. You need to use some engineering judgment to actually assess the probability aspect of how likely is a hazard or how likely is a consequence. But based on this combination of probabilistic and prescriptive risk assessment, there is some important principles from high-risk industries that are important within process safety. Namely that barriers against process hazard shall be independent of and in addition to the control system. So this leads to the no single failure principle, that if you have a failure in your control system, you should have an independent barrier, so you don't have one single failure leading to a loss event. And the other important aspect from these high-risk industries are that there should be 2 levels of protection against any process hazard. It's not sufficient with one barrier. You should have 2 levels of protection that shall be independent of each other and preferably of different technology. This adds robustness to the design. So the framework for a process safety management system is founded on the general laws and more specific regulations that are relevant for the location of your asset or your operation. In addition, there are standards made by various entities that ensure that best practice is formalized. So this is kind of the framework that you are supposed to make your process safety management system within: the laws, regulations, and the best practice standards. Within this framework, an evolving process safety management system should go from a pure standards-based approach, where you blindly implement the standards without fully analyzing or understanding the context of why you have your design this way. From that, you can go to a more compliance-based system where the context is understood based on your facility being custom-made and complex, with its own operating envelope and its own specific hazards. Of course, a good process safety management system needs to take into account both the asset operational and asset lifetime related aspects, and hence you need to ensure that you have continuous improvement based on both operational experience from your own plant and operational experience from similar plants within the industry. But finally, as we have discussed, there are this probabilistic aspect to take into account. So a good process safety management system needs to be based on the actual risks that you have on your site. And the question should always be, how can I better manage the inherent risks and ensure that they are as low as reasonably practicable? So basically what's important to understand here with regards to a process safety management system for any asset is that you do have best practice standards and you do have regulations, but they don't necessarily do the job for you. You need to take into account that the process safety is about safety critical, complex, and custom designed facilities, which are built and operated in asset specific context. So it's not enough to just rely on implementing best practice without actually reviewing with a risk-based strategy or with a probabilistic assessment whether that is good enough on your specific plant.
Thank you, Thomas. So, and this, it will be interesting to discuss so the SIL part and the functional safety part. And now that you have explained the process safety definition and the fundamental principles, the next question is, where does the SIL functional safety fit into this picture? So basically, in the process safety context, it is fair to consider that SIL is a subset part of process safety, which is based on electrical, electronic, and programmable technology. So we are talking about safety instrumented functions. Remember, we refer to a function which consists of a sensor, for instance, a switch or a transmitter, and it consists of a logic solver, for instance, a PLC or a hardwired system, and it will consist of a final element. To give you an example, it could be a shutdown valve. So these functions, safety instrumented functions, they are a part of a process safety. And from now on, so when we discuss process safety, please remember that it also includes the safety instrumented functions. So the things, the theory about it and how it is going to be done, it is all established. I think in the last 15-20 years, we have seen that the different process industries and other industries, they have learned how to deal with SIL things. But these are very broad standards. For instance, when we talk about IEC standards, there are thousands of things to comply with, and especially IEC 61508, which is the generic standard. It refers to IEC 61511. It is the process industry guidance for the standard. So it is not very easy to understand what is a suitable level of working for you and your asset. And for this kind of functions, we are talking about 4 SIL level. So SIL 1, 2, 3, and 4, 4 being the highest SIL level, but it is like next to impossible to see SIL 4 functions in the process industry. To illustrate for you, for instance, if you go to a medium-sized or a large process facility, you're gonna see that based on a drawout assessment, the majority of functions will be either no SIL rated or SIL 1. You may find a number of SIL 2 functions sometimes. Very hardly a couple of special cases you're gonna see a SIL 3 function, but if you see a SIL 4 function, it means that there is something wrong with the design. So it will have to go back to the design table because it is not normal to have SIL 4 functions in process facilities. So this is the SIL part of it, and once again we refer to the process safety together with SIL from now on in this webinar. So this completes the first part with the introduction to process safety and SIL basic concepts, and I would like to continue with the second part where me and Thomas will share our experiences with some essentials. So the first one will be about the process safety management, PSM, and this is once again our experience. So the process facilities and assets, they are very attractive targets for mergers and acquisitions. So we are talking about a steady stream of mergers, acquisitions, and divestments, and it causes reorganizations, right, for this kind of safety critical assets. So what happens is that very competent but limited in numbers resources, they spend time on endless gap analysis, etc., and instead of doing the real work as we hear it on the site when we talk to our clients. On the top of that, there are a set of other initiatives which create extra workload and distraction, right? And what we see is that as a risk driver for process assets and operations, lack of competence, it is the biggest risk driver. It is not the design, it is a lack of competence to operate. Lack of continuity due to all these mergers, reorganizations, and all the other things. And also procrastination, reluctance to implement the complex process safety systems which are imposed by the central organizations. It is one of the biggest risk drivers. It is so complex so that the asset organization, they don't even bother starting, right? And also it is worth to mention that too many initiatives is one of the biggest risk drivers. There are so many initiatives, people don't have time, they don't even want to hear about it, so they just let it be. So what is the key point here? Based on our experience, I think there is a big value on considering the process safety management framework in a decentralized way. For instance, if there is an asset, process asset somewhere, say in Europe, right, which is owned by a multinational somewhere in the United States. So if there is a specific to the point PSM framework for this asset, and if whatever the gap analysis or something like that can be done from the central organization, that will be a huge benefit for the organization so that they are not distracted. Also, this asset-specific PSM framework, it must be very simple, extremely simple, so that you reduce the threshold for the asset organization to do something, right? And another thing is the lack of continuity. So we hear about the reorganizations and all the other things, but when it comes to the matters with process safety, continuity is a must, because we are talking about assets with over 20-30,000 functional locations and components, many different very complex systems. It takes many years to understand what systems we are talking about. So process safety is not something like a learning by doing sport. Hey, John, can you just come over here and look at the compressor systems and process safeguarding? You need to respect the people who are there, who spend 20 years in understanding, and motivate them so that they can do the work. I think it is very important to think about it. And also, I think it is highly important not to embark on any new initiatives, ideas, or fancy tools before giving a careful consideration about how much distraction it can create or what kind of benefit it can give in terms of improved process safety or reliability.
Thank you, Baris. So the first step after you have a process management system in place is to identify the hazards that you have in your plant. And one of the most important and one of the most well-known methods to identify your process hazard analysis or process hazards are, of course, a hazard operability analysis, which is maybe the most widely used system or method to identify hazards within a process design. Unfortunately, it's also one of the most misused analysis to identify hazards in a plant, because it is just one tool in a big toolbox, and it's important for everyone to understand that there are limitations to hazards. It shouldn't be used as a catch-all for all kinds of hazards, as it is based on a process design as identified on process and instrumentation diagrams, PIDs, cause and effect diagrams, and so on. So it is used, or should be used, mostly for identifying hazards related to your process, how you operate your process, and how the process can deviate from the design intent. It's not necessarily the best tool to identify leak sources or causes of fires or ATEX zones. It's also important to understand that it's a subjective tool. It's based on the experience of the team that participates in the hazard. Of course, you need to make a team that has as broad experience as possible, but I think it's been proved several times that if you take two hazard teams and make them do a hazard of the exact same design, there will not be 100% overlap of the identified causes, nor even how they actually assess the consequences of these causes. So it's important to understand that a hazard will be subjective analysis, and that you will not be able to identify all kinds of hazards through just a hazard. So you should use other analyses as well when assessing the hazards at your plant. There are probably as many good recommendations for how to perform a hazard as there are hazard facilitators or people that have been part of hazards. So I won't spend too much time now on giving guidance of how to ensure a good hazard, except I would like to say that in my viewpoint, the most important thing to actually ensure to have a good and successful hazard is to make sure that both the hazard team and also the organization undertaking the hazard understands these limitations of a hazard. So you don't expect the hazard to cover too much. Then you will just end up with best case too many actions because you can't assess everything through a hazard, or worst case, if you only do a hazard, you will end up with a design that has not considered all credible causes of hazard in sufficient detail. As we have already discussed in some of our slides, risk as a concept must take into account uncertainty. This is valid generally when you assess a risk, but within our experience is that specifically within functional safety, which is a discipline that are based on numbers and calculations, this uncertainty is often overlooked. But what's important to understand is that safety integrity levels are given in orders of magnitude. As Baris mentioned, you have from SIL 1 to SIL 4, and there are an order of magnitude difference between each of these SIL levels. The reason for that is to acknowledge that there are inherent uncertainties both in estimating risk and in calculating reliability of a system. Your SIL allocation, whether you do that through the risk graph or LOPA or through other methods, are based on order of magnitude rules of thumb. So your SIL requirements will be based on order of magnitude rules and assumptions, basically. And when you calculate the achieved reliability of your barrier that you have designed, it's also important to understand that that is just a theoretical or a uncertain calculation. Your component failure data will not be exact. It will be based on either SIL certificates, which again is based on a FMICA with theoretical calculations or lab tests, or best case, you might base your calculated PFD on generic data, or even better, if you have similar plants, you can base it on prior use from a plant with similar application and environmental and operational considerations or conditions. But it's still just a figure that you calculate based on certain inputs that are uncertain and that you need to verify later. So I think what's most important is when you talk about functional safety, both allocation of SIL and calculating the achieved requirements of your functions, is to keep track of and confirm the assumptions that you have in your design phase. You might base your SIL allocation on, for example, ignition probabilities, or on the probability that personnel are at a certain place of the plant with a certain frequency, but you should understand which assumptions are conservative and which are not. Which assumptions can you verify during operation and which can you not verify. You shouldn't take a calculated risk reduction or a PFD as 100% accurate answer either. If you have designed a SIF to meet a specific SIL requirement and you calculate that it can meet that to 3 or 4 or 5 significant figures, there's actually no point in that, because the whole functional safety approach is based on order of magnitude. So you shouldn't spend too much effort in calculating very detailed PFDs, as this will be based on several inputs with large uncertainties. So based on that inherent uncertainty, any calculated risk should be taken with at least a grain of salt, and you shouldn't design your barriers blindly based on a calculated risk, nor on a calculated risk reduction. Of course, detailed analysis can often be useful, but it can't always be used to justify a reduction in safety levels. Because if you, through your more detailed analysis, you calculate your achieved PFD to a more level of detail, but you haven't done anything about the uncertainties, then that won't help you at all, basically. So what's important here is, I guess, to highlight that you need robustness in your barriers. For example, if you, through your risk analysis, have calculated that you need a safety instrumented function with a risk reduction factor of 120, or that you found out that you need only a single barrier, given that you have an assumed very infrequent initiating event, it's not necessarily correct to just feel comfortable with a function that gives you a risk reduction factor of 121. There's no yes or no answer. It kind of depends. But of course, it depends on how certain are you about the assumptions and uncertainties that are inherent in both your requirements or the SIL allocation, and inherent in your calculated or theoretically achieved PFD. So that's kind of why API RP 14C and ISO 10418 has this requirement for 2 independent barriers. It is to acknowledge that there are inherent uncertainties in any calculated or theoretical risk reduction. So based on that, when we're talking about functional safety, it's easy to use a safety instrumented function as a barrier that you put in place if you want to achieve a measurable or calculated risk reduction. It's functional safety is related to numbers and to calculating PFDs, so it's kind of easy, or at least assumed easy, to show an achieved risk reduction by using a safety instrument function. But that's not the correct approach, because, as hopefully most of you know and understand, there are a hierarchy in how to reduce risks. It's better to eliminate a risk than to prevent it. So every time you see someone designing a SIF as the first answer against any process hazard, you should know that that's not the best approach. The best approach is if you can eliminate the risk directly by having an inherently safer design, or to design a passive safeguard with less moving parts and an assumed better reliability and better robustness. So this robustness and this uncertainty moves us to our next concept, the concept of independent barriers. As some of you probably know and have seen, the API 521 standard regarding pressure relief operates with a double jeopardy principle. But unfortunately, this principle is sometimes misused and taken to apply for process design in general. This is a misuse that will lead to less robust designs. As I already mentioned, the process safety should combine barrier approach with a probabilistic approach, because you have this inherent uncertainties in your analyses. You should still have barriers in place that are independent of your initiating causes. And compounding on this problem with uncertainty is that most of your barriers, you don't really know whether they work or not until you have had an event where they will be called upon. Of course, that is why you test your barriers and why you have function tests and proof tests of your barriers, but they are not, or at least very seldom, tested to the exact same conditions as would be seen in an actual event. So what we often see is that the double jeopardy principle is misused by saying that, for example, if you have an initiating cause and one barrier having initiating cause and failure of the barrier simultaneously would be double jeopardy. But that's not necessarily the case, because as I said, you don't really know that your barrier is working until you have an event that actually calls upon that barrier. So it's very important to be aware of the latent failures that are within your system. Things could have failed a long time ago, and you don't really know it until you test them or until the barriers are called upon. So based on that, some good barrier design principles is that the fewer moving parts or the simpler the barrier is, the less likely it is to work when you need it to work. It should be fail safe, so if it fails, at least it should go to its safe position. You need some robustness, you need to be aware of the latent failures, and most important, your barriers need to be independent of each other and of the initiating cause. On the right-hand side here, there are two examples. The first one is a typical example from an offshore oil and gas facility where you have some kind of vessel. You have a pressure reduction valve on the inlet controlled by a pressure transmitter that reduces pressure from a pressure source upstream into the vessel. If that control function fails, you have your first independent barrier, which is a high pressure trip that closes a separate valve on the inlet. This is completely independent of the initiating cause, which would be failure of the pressure control function. And you have a secondary barrier, the PZV, which is completely independent of the primary barrier, which is your high pressure trip. The design below could be a perfectly acceptable design if you only do a probability assessment. In this case, you might have, for example, a batch reactor, which you fill based on a level transmitter that opens a valve on the inlet. You might have a timer function that closes the valve again after a certain time, or you might close it on reaching a certain level from the green level transmitter here. You might then think that you have designed an independent barrier. You have a separate level switch that will shut off the feed if your control function does not shut it off. But in this case, the level switch controls the same shut-off valve as is controlled by the control function. So if the cause of high level were that your valve has failed, it wouldn't help you at all to have a separate level switch to try to close the same valve. So this is an example of a not independent system where your initiating cause is not independent from your first barrier. And this is a design that would not be acceptable from a purely prescriptive approach, ISO 10418 or API 14C, but it might be acceptable from a pure probability related approach. This is why it's important to combine these approaches to make sure that your design is robust and to make sure that your barriers are good enough for your specific assets. So from these previous slides, it should be hopefully clear to you that we're talking about concepts of compliance, non-compliance with prescriptive standards. We're talking about what is unsafe and what is acceptable from a probabilistic approach. And especially within functional safety, the ISA 61508 and 511 standards are very large standards with very detailed requirements, and they are promoted in the process industry as benchmark examples of good practice. But what's important to remember is that the legal obligation is not to follow these standards to the letter. The legal obligation is to manage risk to as low as reasonably practicable. And these standards are just a benchmark example of how to do that. And they should be treated as such. 100% compliance with all requirements in any of these standards is really not practicable in the real world. Or it might be practicable, but it requires extensive work. Working towards full compliance is a game of diminishing returns because you will approach full compliance asymptotically. The Pareto principle applies here as well. You might achieve the largest risk reduction by the first effort you put into it, and putting even more effort into it will not really give you that much more risk reduction. So it's always easy for an expert to find non-compliance with these standards for any system. But unless that non-compliance cannot be shown to actually compromise safety, it doesn't really need to be a case of concern, because as long as you have reduced your risk to as low as reasonably practicable, you have met your legal obligations. So there is kind of an overlap between non-compliant designs that are still safe enough. On the other hand, you shouldn't take compliance as under meaning that your job is finished, because even if you can prove that your design is compliant to a certain standard, if you haven't thought about what you're actually doing, that compliance is not really necessarily to make you safe. So basically, I think that the main take from this is you need to use your professional judgment here. You need to show that you've managed risks. Non-compliant might be safe, while compliant might not necessarily be safe, basically.
Thank you, Thomas. And on the matter of compliance, I would like to refer back to my slide about the reorganizations and mergers and so on. It really creates a jungle sometimes when a new company comes with a whole different setup of acceptance criteria and compliance regime for the very same asset which has been safely producing for 20, 30 years time. So it is not really an easy, straightforward topic to discuss. So I would like to continue the discussion on the SIS lifecycle deliverables. So remember, SIF is safety instrumented function, SIL is safety integrity level, which refers to the integrity and reliability of the function, and SIS refers to the safety instrumented system. So basically we are talking about the same things, more or less. So the IEC standards refer to different lifecycle phases. So we are talking about SIS lifecycle management, right? For each life cycle, there are input activities and there are output activities and deliverables which are defined. And in fact, they are defined in very detail. And sometimes it is a problem. These are very detailed requirements, but when you take the detailed requirements to a, let's say, like a synthetic, diesel factory or an offshore oil and gas platform, something like that, it doesn't make sense, right? And the questions we face with are, what are the typical deliverables and what is the right sufficient level of elaboration? So what I show here is the basis package you can recognize in different parts of the world and the facilities. We are talking about a functional safety plan. You need to have a plan. So prepare the plan, right? So I don't think there is any way around that. And if it goes to a third party independent assessment, the first finding they will have that you don't have a plan. And if there are some other mishaps, they will refer back to the plan and say that this is a management issue. So you better need to have a plan about functional safety. So this is one deliverable. Another typical question is like hazard. So how are you going to work with the process hazards and identification of the hazard scenario? Sometimes it goes without saying that you just have a hazard, right? If it's like a process facility of certain size, you conduct your hazard anyway as a part of the project execution. But there are some simplistic scenarios where you can point out this is the hazard, right? Once again, still, I recommend that you take a one-pager or two, make a separate document, and call it the process hazard analysis. At least you know the hazard scenario and you can refer back to this document. Keep it simple, but have it there. SIL allocation is very important step. It is actually the essence of it, like what SIL requirements you're going to assign to the function, right? Is it SIL 1, SIL 2, or 3? Again, there are different methods which are outlined in IEC standard. Typically, we use low-path layer protection analysis as one method frequently used. And you need to have a SIL allocation report. Once again, keep it simple, but have the separate deliverable. And safety requirement specification is the most central document because it bridges the design with the integrity and function requirements to detailed design and testing and operations, so to say. So the safety requirement specification must be there, and it must be a robust document depending on your context. SIL verification assessment is typically also sometimes called like SIL compliance assessment. It is where you sort of demonstrate that your function fulfills the requirements from a design standpoint, right? So you look at the numbers, failure rates, like you use typical different methodologies to make some number crunching to show that your safety instrumented function sort of meets the assigned safety integrity level. And you need to have this document as well. And so how does the vendor and supplier come into the picture? So basically the supplier of the components, for instance, sensor or the valve, they need to send you a document which is called safety analysis report or safety manual. Typically in Norway, especially in the offshore oil and gas business, we call this document safety analysis report, but IEC standards refer to a safety manual. So you need to have this information, and it is mandatory that the vendor must submit this information. If the vendor never heard about this kind of documents or IEC, maybe these are the wrong vendor for you, right? Because all recognized and serious vendors know about this kind of things. They get these questions continuously. So, and then, so one thing you're gonna check about this stuff is that when they receive the technical requisition from you, you need to specify some things early in design, like what kind of SIL level, what other additional or specific requirements are put in place so that they can send you properly. If you don't specify in the beginning, these documents will not come, rest assured. And the third-party functional safety assessment report is very important. It must be conducted by an independent party, which is independent from the project and typically from the organization. It is to make sure that all these requirements and detailed requirements are actually fulfilled. But it is a tricky part because if you find some people who are very theoretical and they don't understand the essence of process design, right? It can easily become a high school exercise. So you need to find the right people with the right experience so that they can conduct it at the right level. And not only that it will be a third-party assurance activity, it will also give you a very good sense of comfort in terms of safety compliance and also knowledge. The proof test procedures are very important, part of it, because it goes back to the operations slide, which I will come to in a few minutes time. And this is also a very important IEC related deliverable. So it is not a maintenance department activity. So this must be linked to safety requirement specification. And it is a safety related documentation for safety instrumented functions. So a quick summary, keep everything as simple as possible. Can it be done in one page or half a page? Make it a one-pager, right? As simple as possible. The longer the document, the messier it is, right? Don't repeat the generic information. If it is already existing information in your company's corporate technical guideline, why do you repeat the same information? It's meaningless, right? Don't repeat the information from IEC. You can just make references. Reduce the fancy words, terms and definitions, especially when we are talking about documents which interface operations and maintenance. Use the words you think they will understand, right? And the final thing is the SRS. What I think it is very important to build it for context, because some companies have already a very well established safety lifecycle management system. So they already know how to do these things. They have different roles, training modules, right? Competence and training programs and tools in place. So basically, it will be enough with the lean, very simple SRS in this case, some sort of bridging document, and only with the specifics of the function. But we have some other clients, and they don't have this kind of systems and tools in place. So we realized that a very lean SRS will not do the work because they have no other documents or systems to rely on. So in this case, so we need to substantiate the SRS to include more information to help the operations and asset team carry out the necessary work with testing and maintenance. So also it is important to remember that there are some other actors in place. For instance, we are talking about the safety system supply. It could be Siemens, ABB, Yokogawa, or similar. They will also receive this information from you, from the design team. So it would be very wise to have a proactive dialogue with the safety system supplier to see what kind of checklist they have, the extensive checklist. What are the questions they will ask you so that you can be proactive and prepare answers or documents in this format. And this was my last part and the summary for the SIS lifecycle deliverables. So I would like to discuss the SIS performance in the slide, and it goes from design to operations. And SIS lifecycle approach is very important. I think it's extremely important to understand the context with IEC, because back in the time, right, before the IEC stuff, you had a good transmitter and you had a good valve and you had a good safety system, right? It was a good function. So the aspects of IEC which are important to realize is that it is performance-based. It always talks about performance, and it is risk-based. And if you don't understand risk and performance right, it's not gonna work. So as soon as we are talking about risk, we are also talking about assumptions. And when we are talking about assumptions, everything is based on assumptions. We are talking about the original design premises with hazard scenario, initiating causes, protection layers in place, risk adjusting factors, what kind of demand mode or rate, which is theoretical. So whatever we tell you, if you have a SIL2 function or SIL3, is based on tens of assumptions for each function. So then on the top of that, there are another assumptions or simplified methodologies coming into picture when we verify that everything is good, right? That's fine, but what happens when the systems are taken into the operational phase, which is the longest life cycle according to IEC? So what we see sometimes, which is very funny, that some people think that if they just are conservative in the beginning, that they put a SIL3 function, it will do the trick. That's nonsense. It has nothing to do with the operations or maintenance. Regardless of the SIL, allocated SIL level, you need to have a proper and to the point operations and maintenance. And in this regard, it's a very broad topic, and we have no time to go into details, but there are two different things, right? When you are in the operational phase, and when you are talking about monitoring the SIS performance during operations, the first thing which is very important, competence and training. And this is a kind of taboo tema among engineers. People are, they get offended when you say that they are not competent. But you really need to be competent about this kind of matters. And the corporations, they must give the required training to their people. And there is no shortcut. So this is the first thing. The second thing is how your company works with management of change and design basis, like when you change the protection layers in place. For instance, let's say that we are talking about an overpressure scenario, right? And we assume that there is a fully sized PSV in place. Then we say that, okay, it's fine with the SIL1 function. But what happens if the premises have changed? And how does the management of change work for your company? So that is extremely important to get it right, and extremely important to get the SIL in the management of change system in its entirety, in the very similar way as, for instance, PNIDs and other safety-related documentation. The last thing is the systems in place for verification of these activities. It must also be in place to get it right. So Very quickly, I would like to round up with the lifetime extension methods, and I'm going to share a very, strictly kept secret. The components have lifetime, right? They have also useful lifetime, and it's a very particular concern because, as it is also stated in the IEC standards, the results from the probabilistic calculations are meaningless, and the probability of failure significantly increase over time. The suppliers say the same thing, we say the same thing, and IEC says the same thing, but you don't agree. Okay, that's fine. But what I can tell you is that the things fail, right? You don't hear about it. Maybe you got a couple of components in your asset. Talk to the suppliers. They will tell you things fail. When they age, they fail. So what I would like to share with you is that based on our experience, if you turn a blind eye on the problem, it's not going to solve the problem with the aging components. And if you show ownership for useful lifetime methods, and if you sort of develop a practical approach, like how are you going to screen the SIF loops, what are more critical, what kind of coming modification projects are in your pipeline, for which modifications, this will be very useful, right? If you do it from a cost-benefit perspective and criticality perspective. And also, if you think like limited, instead of trying to get too much at once, setting up practical goals and achievable goals, I think it will increase the overall safety and reliability level for your process safety. So, and in this context, it is very important to think about the supplier input and the remaining asset lifetime in consideration. This was my last slide, Morten.
So thanks a lot to both Baris and Thomas for giving valuable insights on this topic. So the next part on the agenda is to take the Q&A session. So thanks a lot to all of you for sending in interesting questions for the Q&A. So we have time for some questions now, and we can start with a question from Sandri, and I think this one will be for you, Thomas. It's regarding rehassups. So what about rehassup of operating plants? Is it a valid technique? How often is it recommended to do? And does it make sense to have the technology licensor together in the rehassup session? Thomas, do you have any input?
Yeah, I think it's a valid technique based on the assumption that your last HACCP were the final HACCP based on the theoretical design. Through the design phase, you had some assumptions about how the plant were going to be operated and how your systems were going to be maintained. After you've gained operational experience, I think a re-HACCP is a good way to actually assess whether your plant are operated as it was intended to be operated. Based on that, I think you should at least not do it more frequently than you have new operational information about your plant. I mean, it depends also on where you are. Some countries have a legal requirement to do this every 5 years, which may or may not make sense depending on the level of modifications and the level of changes on your plant. But at least having a re-HACCP after you've operated the plant for a certain number of years is a very good idea to actually confirm that your plant is operated as intended, and to confirm that you haven't really overridden or inhibited any barriers that are critical from an engineering theoretical perspective and so on.
Thanks, Thomas. And when we are talking about HACCPs, we also got the question on whether it's recommended to have 2 teams completing a HACCP independently and then review the results after. I know that the normal procedure is to do a single team doing a HACCP, but Thomas, what's your views on that?
Well, I don't really think I would recommend it. It would be interesting, definitely. First of all, I don't think any operators would pay for that, having 2 separate teams sitting and doing a full HACCP. I think that money would be better spent to actually perform other safety analyses. The money that you use on your second HACCP team could be better spent on actually doing a proper analysis of your leak sources or release points and so on, rather than trying to capture everything in just a HACCP. So I think that the short answer is no. I wouldn't really recommend it. It would be interesting, definitely, but I don't really think it would add much.
Thanks a lot, Thomas. So we also got another question. I'm taking the ones with the HACCP in the same bulk. So we got a question on whether we could elaborate on the application of HACCPs for high voltage electrical systems. Baris, any input from your end?
Well, thank you, Morten. Like the very quick answer is that like HACCP, like I think we are talking about eHACCPs, electrical HACCPs, right? So I think they are very comparable to process HACCPs. We are talking about system boundaries and putting up logical nodes, but this time it will be dependent on using the single line diagrams and electrical design basis is sort of the basis for the HACCP. But my experience is that when we are talking about the electrical HACCPs and also for high voltage systems, the system suppliers in the beginning, they were a little bit reluctant because they say, okay, this is a standard system. What are we going to discuss? But based on my experience, after a couple of rounds, even the system suppliers, for instance, ABB or similar, and also the operators, they find it is a very, very useful forum for identification of deviations and improvement points.
Thanks, Baris. So jumping to SIL and functional safety, and we got a question here on based on the IEC 61511 requirements, is it acceptable to use a non-SIL rated sensor to initiate a SIF? I don't think so, as this would likely compromise the overall SIL we allocated for that specific SIF. Is that correct? Thomas, do you want to share some thoughts on that?
Depends on what you mean with non-SIL rated. There's no requirement in IEC 61511 or 508 to have certified components. Of course, what's important here is going back to having a robust design. The important thing is that your initiator should be independent of your control system, so that a failure of that initiator couldn't both cause the hazard and make your barrier become independent. So I think, again, it depends on what you mean with non-SIL rated. Of course, it needs to be independent of the initiating cause, and it needs to meet your requirements, but that can be met by showing that it's good enough through prior use or proven in use. It doesn't need to have a SIL capable or a SIL certificate saying that it's capable of SIL.
And I can also add one thing on this, Morten. Why do you make it difficult for yourself? I think like if you talk about like simple systems like transmitters, like pressure transmitters and things like that, it is like a mobile phones without camera. How easy is it to find it? You know, most recognized suppliers for safety systems, they have SIL certificates. Find one of them and work with this company.
Good. So we got a question from Amin on may you elaborate on risk reduction factor? How is 120 risk reduction factor or RRF calculated? So Thomas, I know that you are spending a lot of time on SIL calculations, so can you give the short explanation?
Basically, a risk reduction factor is just the PFD inverted. So a PFD of 0.01 would be a risk reduction factor of 100.
That was a quick answer, Thomas. Thanks for that. So we got the question here on, can the SIL rating of a device be readable on site, like a tag number or something like that? Or should it be readable from documents? Anyone with the input, Baris?
I can take it, Morten. So basically it happens that when you go to site, if you go close to a transmitter or something like that, or if you go to like control room, there might be like a label or indication that it's a SIL, it's a part of a SIL rated loop, but it should not be necessary, right? You need to have the technical documentation, and like which shows that like when you look at the component, like the tag number, functional location number, it is a part of a SIL rated loop.
Thanks. So we start to run out of time, but I would like one additional question here, and that's regarding the number of final elements in a SIF. So at times there can be issues with a particular SIF loop having to close multiple final elements, maybe up to, for instance, 5 shutdown valves, given the ESD level assigned for the project. Do we need to limit the number of final elements to, let's say, only 3 number of shutdown valves? Thomas?
I think this goes back to the robust design and taking a step back. From a purely probabilistic approach, it might be calculated to be okay to close 5 fine elements, but taking a step back and looking at your design, you shouldn't really have ended up with a design like that. You could have put all of these, let's assume that it's 5 inputs to a vessel or something, put them in a manifold and have one single valve that you shut down. So, I mean, of course, if you have an operating plant, you might end up with a situation where you need this, but it's not a good design, even if your probabilistic approach kind of shows you that it's acceptable. There's so many uncertainties related to that it would be much better to limit the number of final elements. So taking a more inherently safe or a more simpler design, basically.
Thanks a lot, Thomas. So we are running out of time, and I realize Thomas and Baris, you can talk the entire day about this topic, but we need to wrap up. I see that also we have a lot of questions that we did not cover in the Q&A. So I put the email address for Baris and Thomas in the chat, and if you have any follow-up questions or you want to discuss this further, you can contact them directly. So I would like to thank all of you for joining the webinar today, and I hope you enjoyed the show today. So we are planning for several interesting webinars in the coming weeks and months, and we will also send out a survey following this webinar, so you can give your input and proposal for new topics. So also, if you want to stay up to date on future events, insights, and so on, please follow us on LinkedIn or stay connected through our newsletter. So finally, thanks all for joining the webinar today, and I wish you all a nice day.